And there we go. Okay, so now we're recording. And I'll record this session. We'll make it available to everyone as a review tool to what we're going to talk about. So what we're going to do is talk about analysis and topological optimization using a software called Inspire. I know there's some of you I've seen multiple times, and some of you this may be a repeat depending upon the classes that you're taking. But for those of you who've not seen it before, we're going to go just kind of into a little bit of a theoretical background into what finite element analysis and what topological optimization are, and then we'll hop directly into the using of the software for this. So I always like to start things out by just kind of getting an idea of how many people are familiar with the concepts of finite element analysis. If you maybe run an analysis or two here or there, maybe with SolidWorks, and probably less people. How many people are familiar with the idea of topological optimization? Wow, okay, I'm impressed. Normally we don't get anybody who's, or just in this case, a couple of people. So finite element analysis is the ability to understand the behavior of a complex structure. You may have done something similar to it in just by hand. A lot of times people are introduced to finite element analysis by doing just a simple bar analysis, a two-noded, possibly three-noded bar analysis, where you lock it down on one end and you apply a force to another, and then based upon the Young's modulus of the material and the overall area of the bar, we can calculate the displacement and thus the stress inside of a bar. The problem is once you get beyond something academic and simple, like a simple bar or maybe a cantilever beam, the ability to mathematically solve a situation like that becomes near impossible to do by hand. And so we have to employ computerized mathematical tools to handle that for us. In effect, what you're doing in a very simplified version of finite element analysis is you're solving the spring equation, F equals kx. And of course, you're solving for x. So by reversing that and bringing x to the left, you end up with x equals k to the negative 1 times f. So you can determine the displacement of a string by the inverse of its stiffness times the force. The way that we do that in finite element analysis is through matrix math. What they call a stiffness matrix is computed. And if you've ever inverted a matrix, anything beyond like a 3 by 3 matrix becomes incredibly difficult, and you're talking a massive matrix for hundreds, thousands, or potentially millions of nodes. Inversion of a matrix like that is just impossible for a person to do. So we have to employ computers to do that. And in the old days, we used to define our models usually through punch cards in a machine. Every single node would be identified and then the elements that connect it. Nowadays, we do that graphically through a finite element analysis tool. And what we do is we take a structure, complex or even simple, and we discretize it. We break it down into little elements, little pieces. Because while we can't solve for the entire structure, we can solve for each one of the little pieces. And we treat each one of those little pieces as if it were a spring. You can sit right here. We can just sneak past the projector. No problem. So each one of those little elements is treated as a spring. And once you know how one element behaves, the element next to it you can calculate, or the computer can calculate. And the act of finite element analysis is first the discretization of a complex structure by breaking it down to these little elements, finite elements, and thus the name finite element analysis. And then computing the stiffness matrix, inverting it, and multiplying it by the force. And that's the math that goes into finite element analysis. The way that we do it is we take geometry, we bring it into a preprocessor. And a preprocessor is a tool that we can visualize that geometry and discretize it. We mesh it. We break it up into those little pieces. And those little pieces can either be two-dimensional, little squares and triangles, or they can be three-dimensional, cubes, pi wedges, and pyramid-type elements. And once that's done, then we tell it the type of analysis we want to do. We tell it how it's held in place. And we do that through the removal of what we call degree of freedom. So, advanced question, if I have any individual point, or node as we refer to them, how many degrees of freedom does a node have? Six degrees of freedom, yeah. So any point in space, its location and its movement can be described by a combination of 6 different numbers. Movement or translation in x, movement or translation in y, and movement or translation in z. Those are degrees of freedom 1, 2, and 3. And that handles translation, but we also want to take care of rotation. So degrees of freedom 4, 5, and 6 are rotation about x, rotation about y, and rotation about z. So any combination of those 6 numbers can describe the behavior of any individual node. And that's how the movement and displacement of nodes are calculated. Degrees of freedom can also act to hold a node in place. So a node has the freedom, we call them degrees of freedom because that's the freedom of that node to move. But say, for instance, I'm doing a cantilever beam analysis. So I create a cantilever beam, and I push down on it, and that's the behavior of a cantilever beam. It bends. A diving board is a cantilever beam. To represent that, if I were to just put a force on this, it would just fly off. So to accurately represent that, we have to do something to hold that in place. And to hold that in place, we accomplish that by robbing those nodes of 1 to 6 degrees of freedom. So if you imagine a diving board or a cantilever beam, one end of it is going to be grounded. It's going to be rigidly locked in place. Consider, if I want to do a cantilever beam, I could glue or weld or attach the end of the beam to the wall. If we're thinking about a diving board, the end of the diving board is rigidly locked in place to the frame of the pool. So by removing all 6 degrees of freedom from the nodes on one end, we hold that in place, and then we can apply a force on the other. And then the computer takes over, calculates the stiffness matrix, inverts it, and then does matrix math on it. Take the stiffness matrix, the inverted stiffness matrix, multiply it by the force matrix, you get the displacement matrix. And that's how finite element analysis works. Obviously, it's far more complex than that, but as an easy to understand analogy, that's the basics of FEA. Now, to do finite element analysis in a traditional sense, you have to have a fairly deep understanding of what makes an element, what's a good element, what's a bad element. You have to be trained in the use of a software to be able to bring that geometry in, to discretize it, to mesh it, to hold on to degrees of freedom, make sure those degrees of freedom are oriented properly. For instance, an FEA system relies on a global coordinate system, and that's a default global coordinate system. Which means if I'm moving in X, Y, or Z, that's great. But what if my part's angled a little bit, and it's free to move in this direction? That's not X, Y, or Z, so how can I define that as robbing that degree of freedom? Well, then I have to go and create a supplementary coordinate system. And so it can be a very complex situation to set something like that up. That means that you need that educational background in FE, plus you need education in the software to pre-process it, plus you need education in the solver, and education in what we call the post-processor once the solver's done, being able to visualize those results. Which means FE has always been limited to a select group of people who have that knowledge. And usually those are not the people working on the design at the beginning of the process. They're analyzing things at the end. Which means we have engineers and designers coming up with designs, ultimately feeding them to an analyst who's telling them, okay, you got a problem here, and it goes back to them, and you end up with this massive iterative loop, which can take a tremendous amount of time. And time in a corporate world is also money. And you've got relatively highly paid people, which is continually going through this iterative loop. So time and money. So what Inspire is our attempt, and I'd say attempt, but actually our success in bringing those high-end analysis tools into a framework that's really easy to use. It deals strictly with geometry. And it talks about, or not talks about, but it references things in very common sense terms. As opposed to degrees of freedom, we just refer to it as supports, and we graphically represent the freedom of that to move. And so we can use Inspire to bring geometry in from a CAD system like SolidWorks or CATIA or NX, and we can set up an analysis very, very quickly and be able to run that analysis. Plus then, we have the ability to do topological optimization. And I'll get into a little bit more in-depth description of topological optimization shortly. But let's show you, like I said, I want to keep this as interactive as possible. And I see some of you playing with Inspire. That's awesome. But let's show you how quick and easy it is to do a quick analysis with Inspire. So this is the interface to Inspire. When you look at it, you may see it more along these lines here without these menus on the side. I'm a big fan of turning on these model browser menus, so I come up here to the View and click Model Browser, or I can just click F2, and then I turn on the Property Editor. Once we have a more complex model, we'll see why these are beneficial. But let's do something simple. Let's do that cantilever beam analysis. Now, to do that in a traditional software, I'd have to have the geometry, I'd have to bring it in, I'd have to mesh it, I'd have to establish my degrees of freedom, I'd have to establish my materials and element properties, and then I'd have to establish my load and define the type of analysis I'm doing, and it would take me probably 15-20 minutes to do that in a traditional software. We're going to do the exact same thing in about 3 to 5 minutes here in Inspire. So what I want you to do is I want you to make sure you're on this geometry ribbon here. So the little yellow line under geometry. And this icon right here, our ability to create rectangles. Let's go to the top option, which is corner to corner. It's going to put a grid on the screen. Right now, if you look down here in the lower right-hand corner, you're going to see mine says MMKS, which is millimeters, kilograms, newtons, seconds. Those are the units that I'm going to use. You're actually free to use any unit system you want, and we'll talk about units shortly. I'm going to stick in the millimeter. And you'll see that my cursor or my pointer is snapping to the grid. So I'm going to left-click on one grid point and left-click on another, and I'm going to draw a rectangle, or a square rectangle. Size at this point makes absolutely no difference. So if your numbers don't match mine, don't worry about it. Because what it now does is it gives me these little windows here where I can put in values. So I can type in 100 millimeters. We can make it 100 by 100 millimeters. But again, units in Inspire are as seamless as possible. So say I want to analyze it in millimeters, but I know the size of my cube in inches. I could come in here and type in, let's see, 100 millimeters would be, what, about 4 inches? So I could type in 4IN, and you see it automatically converts that into millimeters. But I'll stick with my 100 millimeters. Now if I right-click, it draws my square, and I'm still in the entry mode. If I right-click again, it takes me out of that, and you'll notice up here, it's highlighted or put the halo around this push-pull. To rotate my part, I'm going to hold down my middle mouse button, and I'm just going to rotate my square a little bit. Just so I'm kind of looking at it, not quite edge on, but a little closer to it. And now if I grab that square with my left mouse button and I drag it to the right, I extend out that square into an elongated beam here. And we'll make this, say, 1,000 millimeters. And now I'll right-click to get out of that entirely, so I'm out of there. And now if I just click F on my keyboard, it fits my model to my screen. So now we've quickly created our cantilever beam. We don't have to rely on the geometry or a CAD package to bring it in. I could bring it in from a CAD package, just coming up here to File, Open, and you see we support any CAD package that's there, but I'm just going to develop my geometry directly here in Inspire. So the first thing, let me turn that off. The first thing we want to do is make sure that this is made out of the material that we want. So if we right-click on that solid, up here at the top you'll see a list of materials. From steel all the way down to plastic nylon. We'll leave it at steel, AISI 304, that's fine. But we've just done something that would have taken a few minutes to do in a preprocessor, which is to define a material for this beam. Now we want to hold on to the end of this beam. So I'm going to come to my structure page here, come to my loads, select this little apply supports cone at the bottom. A support can be placed on a face, on a line, on a point. I'll grab that back face. It's going to give me a little cone. It's on the bottom of that little. So if you look right there, it's the little cones that are supporting it at the bottom. Click those and then rotate around and click that back face. So now that back face is fully locked in place. If I were to double click on that little cone, I get these little triangles. And if I click on one of them, it frees it up to move in that direction. So I've released that degree of freedom. So now it can slide up and down. Of course, now my analysis wouldn't work because my cantilever beam is free to move up and down. But you'll see once I do that, I get these little roller wheels on my icon showing me that it's now free to move in that direction. But I don't want that, obviously. I want it fully locked down in all directions. If I want to zoom in or out, I just push or pull my little scroll wheel. Okay, so now we've locked it in place. Now I want to put a load on here. So I come to my load icon again, and I come to this little force arrow. And on the opposite end from where I put the constraint, if I select that little line or the face, it doesn't matter. So I'll select the whole face. And then we want this to, the force not to compress it, but we want it to pull down. And we see that, at least my orientation, Y is up and down. Pick whichever orientation you want, it doesn't matter. So I'm going to change that to a Y direction, and I'm going to click negative. It's going to pull down, and I'll put 1,000 newtons on that face. I right-click to get out of there, and that's it. You have now just defined a cantilever beam analysis. Everything is all set. Did I bump that? Oh, I'm sorry. Everything that you've done, it now has defined a cantilever beam analysis. Now what we have to do is run it. So we come up here to the Analyze, click the little play button. We'll leave all of the options alone. I click Run, and it will run the analysis. What you need? It looks like a little red, white, and blue to the right there. Click the little play button there. Oh, the force? It's the same icon you were using for the supports, but you click that little arrow, and then put it on the end. Yeah, no problem. And then I did Y and negative. Okay, so what's happening now? Now that we've clicked Run, the interface is taking this geometry, it's sending it to our kind of high-end pre-processing software. It's discretizing it, it's meshing it, it's setting up all of the parameters necessary to run the analysis, and then it's sending it to our solver to run the analysis. Our solver is called OptiStruct. So we're actually using those high-end tools, but we're using them in a very easy-to-use interface. And now you have, if you've never run an FEA before, now you can officially say you've run an FEA. And in a matter of minutes or seconds here, it should be done. We'll get a little green flag above our and analyze. We can click the little green flag, and it'll automatically take us into the post-processing mode. If we click the play button, you see our cantilever beam will deform. And if we want to see the stress, we can come here to the von Mises stress. Yours probably looks like this, not the rainbow, oops, but the divergent. And there's the stress that we see on there. And knowing that steel has a yield stress somewhere in the range of 200 megapascals, and we look here, we see our maximum yield stress is 6.5 megapascals. We obviously are well under any concern of deformation or permanent deformation of failing this. But that's finite element analysis in its most simple form. And that's how easy it is to do with Inspire. You either create the geometry directly in Inspire, or you just open it up from a CAD package. You determine how you want it held in place. You determine where and how much of a force you want put on it. You determine what type of material it's made out of. And we have that library of materials, plus I'll show you how to go about creating your own custom materials. And then you run the analysis. And it will tell you what the deformation is, how much stress is on there, and you can validate your designs as simple and as easy as that. Question?
So I didn't understand what's the advantage of this software over to other FEA packages available right now.
The advantage to this is its ease of use. So what it's doing is it's taking a complex process and making it substantially easier. It has an advantage over analysis tools like those within SolidWorks, because SolidWorks is a great CAD tool, but its analysis capabilities are kind of rudimentary at best, and if you get beyond anything as simple as that, the results end up being wrong, whereas this is using our high-end engine to run the analysis, the engine that's used by Boeing, by Airbus, by the automotive companies for decades now to run analyses and provide trustworthy results. But the big advantage here is the ease of setting up.
So how about the result? The result here is, more accurate compared to other software?
Well, it depends on the. So if you're comparing this to like an Abacus or an ANSYS or a software that is a proven analysis tool, the results should be exactly the same. If you're comparing it to a SolidWorks, which is a CAD package first and an analysis tool second, these results are going to be substantially more accurate. But a proven FE processor, FE solver, Abacus, ANSYS, Dyna, Nastran, a properly set up model in any of those codes should be exactly the same.
So the core of this software for FEM analysis is the same as Abacus?
Well, yeah. So we have our own code. It's called OptiStruct. So for analysis standpoint, our results would be the same as an Abacus or ANSYS. But where we have the advantage after that is we also incorporate optimization in this, and that's what we're going to talk about now. But they don't have the capacity to do optimization, whereas we do. So optimization helps us redesign our part and understand the design of our part to minimize the use of material and maximize the strength of the part. So they're analysis tools, we're analysis and optimization.
So do you consider just S-stress and S-strain, or no, for example, natural frequencies or?
Oh, we can do natural frequencies. So if I come back here to my analyze button, you see normal modes, I could have run a frequency analysis on this as well and pulled the
For
frequencies.
example, for optimization, do you consider other properties like natural frequency or
Sure.
just
Yeah. So if I come here to optimization, I can incorporate frequency in here. So I can say I do not want any frequency to be below 100 hertz, or I want to just maximize the frequency. So absolutely, we could incorporate.
so much
frequency.
of the optimization is possible?
Yes. Oh yeah. Yep. Okay. Okay. So we've run a quick analysis now. But we found out that we've kind of way over-designed our part. It's nowhere near the stress limits of our material. And that means we've over-designed. We put too much material into it. We could make the part lighter and make it just as strong or strong enough to support that. And that's where optimization comes in. And there's not a lot of sense in optimizing a cantilever beam. What it's going to do is just make a hollow tube for us. That's the most optimized structure. So what I want you to do is I want you to open up in those in the files. I want you to open up exercise 1. So this is a part that's prepared for optimization. Topological optimization is a tool where you can take your current part, separate out what we call the design versus the non-design space, and have the software tell you what material is necessary and only what material is necessary to achieve the goal you're looking for, and thus minimize the amount of material you use and lightweight your part. So this part is set up for optimization. This is already set up. The red area is what we call the design space. That's the area that the solver will carve material out of to develop your part. The gray areas are what we call non-design space, or the regions that material has to be there in that shape. And we segregate design and non-design space because in the case of this part right here, it's evident that some sort of rod is going to be going through the end here, and it's going to be mounting in some way to something here. So we need material there. We need a nice hole to be there. And we need a nice flat area to mount. So we separate those out as what we call non-design space, the region that the solver can't touch. But the big red area, the solver will carve away at that. We'll determine what material is necessary and what material is not necessary. Additionally, some constraints have been put on here. This red plane is what we call a symmetry plane. It says that this part has to be symmetrical across that plane. So both sides of this part have to be symmetrical, and what's most applicable to this class is this blue rectangle here. I have said in every class I've ever taught about optimization that the most incredibly designed part that has ever been created. The thing is the lightest part ever. It costs next to nothing. It's stronger than anything that's been created ever. It's completely and totally useless if you can't make the thing. And that's where design for manufacturability comes in. We not only have to design parts that do the job, we design parts not for just the fun of designing them. We design parts because ultimately they have to be made and put into something, whether it's a car or an airplane or a motorcycle or a Mack truck or whatever. We design parts to be manufactured, to be used. So we have to be cognizant of the fact that our designs have to be manufacturable. And what ends up happening with optimization does a load path analysis. It determines how the load is progressing through the part, puts material just where that load is, and removes all the rest of the material. The problem is, in many cases, in fact, usually in most cases, that tends to end up with a very organic and pocket-filled design. So it can be hollow in certain areas and have undercuts. And those types of parts, while they are structurally amazing, can't be made in a conventional design or a conventional manufacturing process. Forever, we have been limited to casting, stamping, and extruding as our main tools for manufacturability. Casting or stamping, you imagine you have a flat plate of material, you have a punch on one side and a die on the other side, which is the reverse of the punch. The punch comes down, pushes that material into the die, exceeds the yield strength of the material so it permanently deforms, and you end up with a shape. A large portion of the cars that you drive are made in that way. If you look at your hood, at your body panels, at many of the brackets inside of it, they're made in that way. And usually it's a multi-stage process where they push some of it in and then maybe bend something out and pierce a hole and push more. It's a very complex process, but the bottom line is it's a stamping process. And if you imagine taking a punch and pushing it down into a die, once that punch comes out, that part has to come out of the die, which means you can't have a part that's shaped like that. And you can't have a part that's shaped like that unless you take and turn it on its edge. But there are limits to what you can manufacture. Casting is the same way. Casting, you're pouring a molten liquid, be it plastic or metal or whatever, into a cavity, and then you're allowing that to cool, and then you have to remove that from that cavity. So there are limits to the manufacturability of it. You can't have undercuts, you can't have hollows inside there. There's no way to pour something into a mold and have it hollow on the inside. It just can't be done. Extrusion is a method in which we take a liquid or a semi-liquid and we push it through a shape so it extrudes out into a shape. If you ever had a Play-Doh toy when you were a kid, where you take the Play-Doh and you put it into a little bucket, and you put a little shape in front of it, and you push down on the handle, it puts out little triangles or diamonds or new shapes. That's extrusion. Well, extrusion means you have to have a continual cross-section all the way through, because you're just pushing it through a shape, and each subsequent cross-section is exactly the same. So those are limits to what our parts can look like, and depending upon how you're planning on manufacturing it, your part has to look like something that can be manufactured by that. That's what the design for manufacturability is all about. Creating awesome designs, but creating awesome designs that can be manufactured. And I know probably in the back of your heads you're thinking, well, hey, what about 3D printers and additive manufacturing? Yeah, they are absolutely changing the world. You are sitting at the crux of a massive revolution in manufacturing technology. I was at GE Additive Manufacturing, GE Aviation at the end of last year, and they are pouring a ton of money into additive. They are building a manufacturing facility with 10 laser sintering 3D printers, additive manufacturing, with a meter by a meter by a meter bed. So they can make a part that's 3 feet by 3 feet by 3 feet. And they are putting a ton of 3D printed parts into their jet engines. It's revolutionized what they can do, because they need a very complex flow path for the gases and for the fuels to go through there, something they could never do before, and now they can with 3D printing. The problem is they're making hundreds or thousands of jet engines a year. They're not making millions like we are with cars. So cars, automotive, we're kind of stuck with the traditional manufacturing technique. But while additive is changing the world and allowing us to create things that we never have been able to create before, even they have manufacturing requirements. When you're manufacturing an additive, whether you're doing, when you've got one of those little desktop devices that takes and melts plastic and builds up, or whether you're laser sintering, which is a really cool process if you've never seen it, still, you're building up and up and up and up. Which means you can't have parts that are angled out too far, or you've got nothing to build the next layer on. So there are limits to that too. So even with additive, which is creating things that are just absolutely amazing, there are manufacturing requirements for there too. So design for manufacturability is critical when you're using a software that is helping you understand the shape of your part. And that's what this little blue rectangle is doing. It is, you'll see if we come up here to our shape controls, we have single draw, split draw, and extrusion. Single draw is that punch that I was talking about, punch and die. Or just a simple pour liquid into a mold. Split draw is when you're coming at it from both sides. It allows a little more flexibility because you've got two molds that are coming to form a cavity and then can split apart. And then extrusion. Well, this part is going to be manufactured in a split draw process. So imagine we take two molds, we bring them together, it forms a cavity, we fill it up, we separate the molds, and the part has to come out. So we can incorporate the design to manufacturability right there in our optimization process. So to see what this can do, come to the Optimize button here. We're going to run what we call a maximize stiffness optimization. It's going to maximize the stiffness by leaving only 30% of the volume of the design space. And if you're in millimeters, make sure that this thickness constraint says 30 millimeters. And if it does, then click Run. And it'll start running the optimization. So while that's going on, I'm going to open up to any questions here. I know this is an insanely abbreviated section. We've just kind of run through things. The lab tonight will have a little more in-depth how to go about doing stuff. Plus, if you go through those manuals and the model files that were provided to you, at the end of each section is a step-by-step instruction for how to do each one of the different sections. It'll break it up into geometry creation, setting up an analysis, setting up an optimization, connecting things. You have that opportunity as well. So does anybody have any questions about the concepts behind topological optimization and how design for manufacturability works into that? Yeah.
How does Inspire work with like thermal controls and like heat transfer and stuff?
So it's not heat transfer. So this is what we call linear static. So it deals with material in the linear elastic range of the stress strain curve. And it's an instantaneous analysis. So since all we're doing is solving F equals Kx, there's no time in there. So heat transfer requires time because it has to progress through. So we don't do heat transfer in here. We do incorporate heat as a thermal load, but then that's just the load using the coefficient of thermal expansion. It will expand the part, and then because of the deformation, it induces stress in there. So we do allow thermal, but it's just a simple delta T in that case. If you want to do heat transfer, we do support that with one of our other solvers, but we don't do optimization against it. Optimization right now is strictly linear. If you want to do optimization on a dynamic situation, then there is a way to do it with OptiStruct itself, not with Inspire, and it's what we call an equivalent static load method. What they do is you take your dynamic behavior and you establish a static load case that results in the same behavior, and then you optimize to that. Okay. But we can't do that in Inspire. So we'll give all the systems a chance to resolve that. It looks like someone's playing with polynerves over there. That was awesome. Yeah.
It takes time.
Yeah, it takes a little bit of time. It's not too long, but it takes a little bit of time.
Yeah.
And just once everyone's starting to see some results, then we'll pop the results on here and talk about those. And it'll take us right to the end. But so optimization. Our goal with optimization is not to replace the engineer. The goal with optimization is to supplement the engineer, provide them information. What I can relate that to, let me, since I don't have a wipe-off board here to write on, I will, do I have, where is my, oh, there it is. So, normally I do this with a pen and tablet and draw a little bit better on there, but I'll do it with my mouse. So if I come here and I create a quick graph, oh, I need my, so if I create a quick graph here, and down here, we'll say this is time. When you start on a design project, at the beginning of the design process, you have, and we'll say this is 0, and this is just plus up here. So an increase. We won't label this axis. So at the beginning of the design process, you have the absolute most freedom of design. And then as time progresses, your freedom of design follows a path like that. So the further along the design process, the less freedom you have to change your design. Ultimately to the point that you settle on a final design and then you're done. Well, the paradox is, at the other end of this, the knowledge that we have about our part does something like this. So as we move through time, the knowledge of our part increases. So at the point in time where we have the absolute most freedom to change and affect our design, we know the absolute least about our part. And so we run tests. The Apollo space program is the one that I always refer to. Before they built the Apollo rockets and sent people to the moon, they didn't even know they could do it. So they would come up with an idea, and they'd test it, and they'd test it, and they'd test it. And once they were set with that, they'd lock it in, and then move on to the next problem, the next problem. Each time they made a decision, they limited their choices to change that. Because, of course, we had this 1969 deadline to put people on the moon. Their choices became limited. But each test they ran, each idea they devised, they gained more and more knowledge. The idea of a software like Inspire is not to design parts for you, but to do this. Take this knowledge curve and shift it like that. So at the beginning of the design process, where you have the most freedom, you also now have much more information that you have. This is not to design a part for you. It's to help you understand what a part should look like. And I'm seeing people being done, so it's time to reveal the answer here, which is this. This is what topological optimization has come up with. And if I double-click on this, you see some of these little members here are a little weak, so I'm going to use this slider bar to shift it over. And now this is a well-designed part. The thing about topological optimization is it gives you the ability to create designs, to understand designs, to create parts that you never, ever would have come up with on your own. No engineer would have ever come up with that, because we can't look inside the part and see how the load is progressing through there. Topological optimization generates these very organic-looking, very outside-the-box looking designs. And because of the, what time do we have still?
Oh, we still have 10 minutes.
Okay, good. Because we incorporated that manufacturability constraint in there, not only is it a wickedly cool design that is strong and light, it also can be made. That's what topological optimization is about. You're going to start seeing things like this in automotive. You're going to start seeing them in aerospace. You're going to see these organic-looking designs. because people are beginning to develop more and more trust in software like this and begin to step outside the box and create things that just aren't orthogonal shapes. That's what topological optimization is, and the ability to incorporate design for manufacturability in it is critical, even if we're looking to 3D print things. And from here, now I can click the little Analyze button, and it would take this shape and run another analysis on it, so I can make sure that it achieves the goals that I set forth on it, that it doesn't exceed the yield strength of the material, that this part is manufacturable, or that this part is structurally intact, and then I could take this concept back to a CAD system and begin to develop a part from it. Am I going to just take that as is and create it? Probably not. I'm going to engineer it. I'm an engineer. I'm not just going to let a software determine my part for me, but I'm going to use the information that's telling me about where material should be, and I'm going to use that to help me design a part. Questions? Again, in the lab tonight, we'll go more in depth into the button pushing. Yeah, go ahead.
Is there a speed?
Yes. Oh, thank you. Thank you for reminding me about that. Yes, and I actually have internet access now, so I can show it to you. You come here. And right there, get free student edition. So you click on these happy-looking students here. It'll pop up a little window where you can click download now. Oh, there we go. Okay. It's going to open up this little interface where you're just going to put in your information, your name, the school, the department you're in, when you expect to graduate, your school email. You have to use your school email, your .edu email address. That's how we verify that you're actually a student and not just somebody looking to scam our software for free. And then it'll say Ethernet host ID. So in your computer, you've got an Ethernet card, and it has what we call a MAC address. It's a unique address locked to that particular card, and it's the way that we lock a license to your thing. If you click that little Find Your Host ID, it'll pop up a little utility that will report it to you. When you click Apply, it will send back an email to you just to verify that the email address is valid. Sometimes they get tossed into a junk folder, so keep an eye open for it. It should happen within about 5 minutes, and then usually within about a day or so, you'll get your, they'll send your license, how to install the license, and how to download the software. We have some limitations on our other software that you can get through the student edition, some node limits, but Inspire is the full version, the exact same version that all of our corporate customers are using. And we also break down all of the downloads, so you don't have to download our entire suite. You can just download Inspire. But absolutely do that. It's a year-long valid license, and then you just apply for it again next year. And honestly, as long as you have a valid student ID or a student email address, you can continue to download it until you don't. But the only other thing, when you say the terms and conditions, when you click little approve, it makes you swear, hold your hand to your heart and swear that you're not going to use it for any corporate purposes. You're limited to use it for nonprofit academic situations. But other than that, there are no limitations on it. So please get that. They'll approve it usually within a day or two, and you can start running the software immediately. Yeah.
What if you graduate in May? You still keep it for a year?
Oh yeah. Once you have the license, it doesn't go away. It's a year-long license, and then, like I said, as long as you still have an EDU email address, all they look is make sure it's an EDU email address, and they'll send you a license so you can apply for it again. So. Yeah, I'm kind of of the firm belief that I really don't care as long as if you're interested in the software, we want to get it to you. As long as you're using it just for academic purposes, I don't care whether you're a student or not. So, But yeah, just it's a year-long license once you have it. Okay, so that's it. I'm here to help with anybody that needs any assistance. And then I'll be doing the lab tonight, and I'm also in town through tomorrow. So if you have any questions, please pass it through Dr. Zhang. He knows how to get in touch with me, and I can work with you. If you're working on Inspire and you've got some issues working on it for a student project or anything, you can pass the question to Dr. Zhang. The easiest way that I find to provide support to university students is to kind of filter it through the professor. So send your questions to him, he can get them to me, and then I'll get the information back to you. Yeah. So,
Okay, let's thank Eric again.
thank you very much.